What we're going to think about today and talk about today is something called percent yield. Percent yield. I think we skipped over just a couple slides there where we practiced with Avogadro's number, but I feel pretty comfortable moving forward with that. So we're going to talk about something called percent yield. I want to give a big picture of what does the word yield mean. Where might we see the term yield used in other areas? Maybe in like crop harvest, right? If we expected to grow 50 pumpkins and instead we only grew 40, what would our percent yield be? Right? If the expectation was 50 and we grew 40, it would be an 80% yield, right? We didn't yield what we expected to yield. We yielded less than that. If we were expected to grow 50 and we grew 100, right, we would have a 200% yield, right? We outgrew our yield. So when we talk about yield, it's talking about our production. What were we expected to produce? And so everything we've been calculating thus far has been just that, a calculation. It is theoretical. And so I want you to highlight that, circle it, do whatever you need to kind of remember that. But everything we've been doing so far has been theoretical. And that means it's the expectation for what we think would happen if everything goes perfectly in the lab. But that doesn't always happen that way, right? Sometimes when we go into the lab, we have issues with measurements, we have human error, we have compounds that are imperfect or impure. And so we have things that affect our actual outcome in the lab. And so everything we've been doing so far is just that. It's theoretical. It is what is expected to happen. So when we look at calculating our percent yield, we're going to calculate what actually happens in the lab. Okay? And so to determine our percent yield, how do you find the percent of what you get on a test? What do you take? What math do you do to find that? To calculate your percentage on a test, what do you do?
Amount of problems.
What you got divided by what you should have got, right? Or could have got. So you take your part divided by the total, right? Or the expectation. And so the percent yield is going to be exactly like that. In order for us to find the percent yield, we're going to take the actual yield, which maybe comes from the lab, over the theoretical yield. So actual over theoretical. Actual yield over theoretical yield. And what do I have to do to get at that number into a percentage? I multiply it by what? 100, right? I get that into a percentage by multiplying it by 100. So I'm able to calculate my actual yield based on what I should have gotten, or vice versa. Maybe I go into the lab and I only produce 32 grams and I was supposed to get 37 grams, right? And I'm able to calculate my percent yield from that. So it's a relatively simple calculation, but we need to understand the actual lab maybe is something that we measure or we look for, but the theoretical yield always comes from our t-chart. Okay, always, 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 our theoretical yield comes from our t-chart. T and T. Okay, theoretical yield comes from the t-chart. We have to remember that. We're always able to calculate theoretical yield. Okay, balanced. It's already balanced for us. This says how many grams of water will be formed if 36.5 grams of oxygen are used? And then what is the percent yield if only 7.95 grams are formed? So the first part of it asks us how many grams of water will be formed. That's kind of like the expectation, right? That's going to be our theoretical yield. But again, we're going to write over here. We're looking for grams of water, and we start with 36.5 grams of oxygen. Okay? And we're going to start with what we know. 36.5 grams of O2. We're going to get rid of grams of O2 and go to moles of O2. In this part of my chart, is moles going to get a 6? No, it only gets a 1 because we say 1 mole of O2 weighs 32 grams. We're going to keep on marching here, right? And if I have moles of O2 up here, then that means moles of O2 needs to go on the bottom. Moles of O2, and here's where we can make our switch to now focus on water. And this is our mole ratio step. Okay, O2 is going to get a 6, and H2O is going to get a 3. Now, I haven't heard this question yet, but it is a question some people tend to ask. Well, if this is 3 over 6, can't we reduce that down to 1 over 2? And the answer is you could, but is it really a necessity? No. We're putting it all into our calculator anyway, so rather than run the risk of incorrectly reducing, let's just keep them, right? And that way we can really see our mole ratio clearly. Okay, and then if moles of H2O is here, what needs to go on the bottom right here? Yep, moles of H2O. And I want to end up in grams of H2O. Remember, that's my question mark. And so I'm going to come up here and say 1 mole of H2O is, I think, 18 grams. Okay, so let's run the math and see what we get. 36.5 times 3 times 18 divided by 32 divided by 6. That gives me a value of about 10.3 grams of H2O. Okay, and so here's my question. First of all, did we all come up with something around there? Mm-hmm. Now, is that my actual yield or my theoretical yield? Theoretical, because it comes from my T-chart. So that's my theoretical yield. Now it says, what is the percent yield if only 7.95 grams are formed? So what's that going to be? What's that 7.95 going to be?
Actually.
That's my actual yield, right? You can almost say it that way. If 7.95 grams are actually formed, right? So now if I want to find percent yield, I'll come down here and say the percent is equal to the actual divided by the theoretical, and I need to take it times 100. I don't always write that in there because we know how to get it into a percentage, but maybe I should. And I get about 77%. I get about 77%. So I made about 77% of what I was expected to make. Now, should we, could we, might we end up with a percent yield higher than 100%? It's possible. It's possible, right? In real life, in our high school labs, it's very possible because maybe there's impurities in our materials, or maybe we're using tap water instead of distilled water, or whatever it might be, right? It's possible. But in our problems, that might be a red flag that we should go back and check something just to make sure, right? It's possible, but it's unlikely. That's not the goal, right? The goal would be 100%, not over that, okay? Let's try another one here, okay? It says, if the reaction of 40.8 grams of C6H6O3 produces only a 39% yield, how many grams of water will be produced? So we need to walk through some context clues first of all here. It says 40.8 grams of this compound. So is that my starting amount? Is that my actual yield? Is that my theoretical yield? What do we think? It's my starting amount. It's my starting amount. So I'm starting with 40.8 grams. And it says it produces a 39% yield, but it doesn't directly tell us what is a 39% yield of what, right? We have two possible products here. So a 39% yield, how will I know which one it's talking about? Look at the rest of the question. It says, how many grams of H2O will be produced? So that essentially means I'm looking to solve for my actual yield of H2O, which means this must be the percent yield of H2O. Do we see how that works? Okay, I need you to make sure that we can read those context clues and feel confident in what we're asking. Okay, do we feel okay with that? So the first thing I need to do, can I start with my percent yield equation first, or do I need to work with my T-chart first? I need to find out my theoretical yield in grams of H2O, right? I need my theoretical yield first. So I need to look for grams of H2O. So let's start with what we know. 40.8 grams of C6H6O3. Grams of that compound to moles of that compound. And here, moles will get the 1. What number will go with grams? It needs to be the molar mass, right? Grams always gets molar mass. So 72 plus 6 plus 48. What did you get for molar mass here?
126.
126, agreed. So now we're going to bring down moles of C6H6O3 and switch over now to moles of H2O. This is going to come from our reaction. So C6H6O3 is going to get a 1, and H2O is going to get a 3. And we're going to keep getting rid of moles of H2O and go to grams of H2O. 1 mole is 18 grams. So now I can just do my math. 40.8 times 3 times 18 divided by 126 gives me 17.5 grams of H2O. Tell me if that's close to what you had. Yeah? Okay. And then if we are going to look at the rest of our question, it says we have a 39% yield. This 17.5, it must represent our what? The theoretical yield. And our goal is to solve for the actual yield of water. Now, when we go to solve our problem, right? Remember how to get it from a decimal to a percent, we had to multiply by 100? We're going to reverse that here to start. So we're not going to use 39%. We're going to use 0.39 equals actual over theoretical. Okay, we're going to like reverse that and get that percentage back to a decimal place. Because if we just use 39, it's going to make our actual yield like a crazy number. Way too high. So we need to take, what's the algebra now to solve for A? What algebra am I going to do?
Multiply each side by 7.
Yeah, I'm just going to multiply each side by 17.5, right? Times 17.5. That cancels it. I take this times 17.5. There's 0.39. And I get an actual yield of around 6.82 grams. My actual yield is somewhere around 6.82 grams.